Hi, my name is Nasnjavsky. This is a class called Discrete Structures. This is an introductory lecture to the class called Discrete Structures. The class is taught at Brooklyn College, part of City University of New York. It's a general prerequisite for a lot of computer science classes. It's a nice class, lots of fun, many different topics that are usually used in other computer science classes. So we're going to learn a lot about sets and logic and proofs and sequences and graphs and stuff like that. Probability, maybe a little bit, depends how much we cover. Infinite sets, etc. So today we're going to have a general introduction to the class, and then we'll do section 1.3, some special sets. Okay. Like I said, the class has a lot of prerequisites for other computer science classes. A lot of the things we're going to learn here, you could have seen already in a pre-calculus class, or nowadays even in a high school class, like logic is taught in high school. But it's a nice reintroduction, or a nice way to do it. The only way to do this stuff is to do lots of homework problems. I'm going to attach below a page of homework sheet problems, and then every single section we do is going to be another video, and then another video with working out the answers to the homework problem. The book we use is called Discrete Mathematics, 5th edition. It's a good book by Kenneth A. Ross and Charles B. Wright. And basically, we teach towards the homework problems, and but the book is extremely readable without me, and it's very easy to attain this book. So try to go out and get it. Okay. The word discrete means separated, so we deal more with the natural numbers and things like that, as opposed to what you learned in calculus, where you deal with real numbers, which is continuous and ever changing, ever going. Okay, so that's enough for the introduction. We skip section 1.1 and 1.2 simply because they're either too easy or just not interesting enough. So the real meat of the course starts in section 1.3. So section 1.3, some special sets, and we learn a little bit about different sets. So the first thing we do is go through a hierarchy of sets of numbers, namely P for the positive numbers, 1, 2, 3, 4, ... Okay, and it's obvious what that P shows up all over. You want to say how many brothers you have, how many siblings you have. They're one of that. Okay, but there's also the natural numbers, which is the positive numbers plus 0. And there's some historical thing about 0 not being a number, etc., etc. Anyways, and also in some books they don't use 0 as a natural number, but we're gonna have 0 as a natural number. Okay? Now, that's fine, but let's say you want to talk about, for example, if somebody says to you, you have 5 oranges and someone takes away 8 oranges, how many oranges do you have? Well, that question doesn't make sense, because if you have 5 oranges, nobody can take 8 oranges from you. But the negative numbers were invented during the medieval times, and so we need those two to discuss those two. So we have Z. Z stands for some German word, Zeiten or something like that, and this is not only the positive numbers but the negative numbers too. So -3, -2, whole numbers. So this is called the integers, -1, 0, 1, 2, 3, and this goes on forever. Okay, and these are also called the counting numbers. Okay, great. So with Z, you can talk about not only things you own, but also how many things you owe to other people. We could talk about directions, positive, negative, things like that. as time went on, they started talking about fractions or rational numbers. And this is m over n. This is a description of the set, m over n, such that m is in Z, n is in Z, and n is not equal to 0. Okay, so these things are called rational numbers or fractions. Okay, and that's fine and dandy, but if you had a square, if you have a square and this side is 1 and this side is 1, this side becomes square root of 2. Square root of 2 is a wonderful number. The only thing is, it's not a fraction. I'm not going to prove that now, but we have to go on. And so the next thing we talk about is the real numbers. And the real numbers, your teacher in 9th grade started off like that. And that's 0, that's 1, that's minus 1, and every single number in between, including square root of 1, square root of 2. So these are called the real numbers. Part of it is the rational numbers, but a much larger part of it is the irrational numbers, numbers that cannot be written as the square root. Okay? Mathematicians go on and they talk about other types of numbers, like the complex numbers, and the quaternions, and the octonions, lots of other things which we are not going to deal with at all, but there is this sequence, this hierarchy of types of numbers that are useful. Okay, let's focus now on sets in particular, how you describe them. Notice here we listed them, although we can list an infinite set. Here we listed them, here we describe them. They're m divided by n, and we give a description of what m is and what n is. And here we just set it. Okay, but let's move on to other things. Okay. Given a set X and an object or element B, we could write B is in X, or B is not in X. So we write it with symbols: B member of X, B not a member of X. Okay? And a large part of this class is getting used to symbols. We like to get used to symbols and talk about things. So let me just give you an example. 58 is a member of the natural numbers. Minus 58 is not a member of the natural numbers. That's a negative number. And only has positive whole numbers. Okay? But minus 58 is a member of Z. Okay? And we can talk about students in class. So we'll call that C for students in class usually. Okay? And then, you, if you're a member of this class and you're not just listening in from some other class, so then you are a student in the class. And if you're living some other country, welcome to our class, but then you are not a student in our class. Okay? Great. So this is just using this notation. This is a Greek letter. That's another thing you have to know about this class. Greek upper and lowercase letters, it would be very helpful if you learned those letters, because they're used all the time here. Okay? And it's, again, this is all prerequisites for a lot of other classes that you will go through in life. Okay? Now, there are two ways to write sets, and I showed this before. You could talk about 3, 5, 7, 9. You can talk about a set by listing off the elements, and so we can do that. Okay, and again, what happens if the set is infinite? It's hard to list off the elements in a finite board, but you make ... to understand that. Okay, another thing we can do is we can describe the set. So instead of this, we can write n such that n is odd and 1 is less than n, which is less than or equal to 9. Okay, so this is one of many possible descriptions of that set. So again, we can list a set or we can describe a set. And now I want to talk about different things about sets and how they work. So let's go through it. Okay, let's go through it. Okay, let's look at sets S and T. You have two different sets, okay, and you write S is a subset of T, okay, and you denote it like this: S subset T. That's the way you write it, okay. And when is this true? If, so now we're describing and giving a definition. What does it mean for a subset? If every element of S is also an element of T. Okay? When you have that, you say S is a subset of T. Okay? Let's write it another way. You write it another way. You say X member of S, every element of S, implies, this is true, S is a subset of T, if X element of S implies X element of T. Again, our goal is always to symbolize things, make things into symbols. Symbols are clearer, they make things better and easier. So you would write the same line as X member of S. If X is a member of S, then X is a member of T. So we've totally eliminated any English here. X is a member of S implies X is a member of T. Okay? So for example, you have the set of students in the class, you have the set of girls in the class. The girls in the class are a subset of the set of students in the class. Okay, why? Because every girl who's in the class is a student in the class. Okay, and you, again, we're just using the word subset as it is in English, but we're being exact and formal in the definition of what it means. Okay, great. So another example, the set 5, 9, okay, is a subset or equal to 3, 5, oops, sorry, 3, 5, 7, 9. Okay, let me give you another subset. Why is this true? Because 5 isn't here, 9 isn't here. Okay, 3, 5, 7, 9 is a subset, or that little line means or equal to 3, 5, 7, 9. Okay, why is this true? Because 3 isn't here, 5 isn't here, 7 isn't here, 9 isn't here. Okay, great. Okay, so now we have the definition of what subset is. Now we talk about something else. Again, this might be simple, but every beginning we start off nice and easy. Okay, let's look at two sets. Let's look at sets S and T. S is equal to T. We write that as S equals T. If S is a subset of T and T is a subset of S. Okay? Okay? Which means every element of S is an element of T, and every element of T is an element of S. That's what it means for two sets to be equal. Well, from this definition, what we get is the following. The set 3, 5, 7, 9 is equal to the set 9, 7, 3, 5. Why? Because every element of this set is an element of this set, and every element of this set is an element of this set. So these two sets are equal. What we get from this is that when we talk about sets, the order of the elements is not important. We don't care about the order of the elements. Later on we'll talk about sequences. By sequences we do care about the order of the elements, but by a set we don't care about the elements of a set. Okay? One other thing we learned is the set 5, 7, 7, 5, 3, 5, 3, 3, 9. Okay? That set with a lot of repetitions is also equal to 9, 7, 5, 3. Okay? Let's see why this is true. Why is this equality? Because every element here, 5 is here, 7 is here, 7 is here, 5 is here, 3 is here, 3 is here, 3 is here, 9 is here. We can even put another 9 here. And we could do the same thing here. 9 is here, 7 is here, whatever's in here is in here. 3 is here, 5 is here, 9 is here. So since whatever's in one set is in the other set, so we say these two sets are equal. What this means is repetition is not important. Repetition is not important. Okay? It doesn't matter how many times you repeat an element, it's the same set. Now, we usually, when we list a set, we don't deal with repetition. We don't mention repetition, but that's okay. Okay. Now, given this definition of subset, we can write those beginning sets. We saw P is a subset of the natural numbers, which is a subset of the natural numbers, which is a subset of all integers, Z, which is a subset of the fractions, which is a subset of the reals. Okay? Okay, great. Okay, they're subsets of each other. Great, let's go on to something else. S is a proper subset. Proper subset, so that's a special type of subset of T if S is a subset of T, but S is not equal to T. Okay, and we write that as, so proper subset means really smaller. So what, in other words, there's every element of here is in here, but not every element of here is here. Okay, so that means this is really big. This contains elements that are not it. We also write the same thing, proper subset, as follows. We cross out the line, so they're not equal. Okay, sometimes we write it like this, S subset of T. It's like when you have two numbers, you have X and Y, and you want to say X is less than or equal to Y, X is less than but not equal to, and you could also write X is less than Y. Okay, so you can leave that out. Okay, now going back to these sets, P is a proper subset of n because P doesn't have 0, n has 0. This has the natural numbers, this has the positive whole numbers, this has the positive and negative whole numbers, so this is more. This has the positive and negative whole numbers, but it doesn't have fractions. The number 5/3 is in here, but not in here, so it's not. And this has the square root of 2, which is not a fraction, and it has many other numbers, so they're not equal. So all these are proper subsets. Okay, let's do another one. 3, 5, 9 is a proper subset, but not equal to 3, 5, 7, 9. Okay, because this has 7 and this doesn't. So the only non-proper subset is the entire set itself. Okay, great. For a second. Okay, now that we know all about these sets and these symbols of element, subset, proper subset, equal, I want to do some an acute example. So here's a nice example. It's a weird example. Consider the set S, which contains the letter A, the letter C, the number 4, the set 5, 6, the number 7, and the set containing D. Okay, so a set can contain anything, including other sets. However, first question, how many elements does this set have? Well, 1 element, 2 elements, 3 elements, 4 elements. This is a set that contains 2 elements, but it is one set. So 1 element, 2 elements, 3 elements, 4 elements, 5 elements, 6 elements. Okay, so this only contains 6 elements. But now we can talk about different things. For example, the set 5, 6 is that a subset of S? It's a question mark. Is it a subset? And the answer is no. Why? Because what does it mean to be a subset? Well, here's a set, and every element of this is an element of this. Well, 5 is not an element of this set. 5 is an object of this set. I'm sorry, 5 is not an object of this big set. 5, 6 is out. So this is not true. What is true is 5, 6, the set containing 5, 6 is an element of S. So that's an interesting distinction. Okay, let's do this. D is not an element of S. There is no D here. However, D, the set containing D, is an element of S. Okay. Here's something that is true. The set containing 5, 6. So let's go through this. Here's a set. It has 1 element, the set containing 5, 6. It is an element here. So this is true. Okay. How about this? Is D a subset of S? And the answer is no. This whole thing, this statement doesn't even make sense because this symbol demands a subset here and a subset here. This is not a subset, this is an element. Anyway, so this is not true. Okay. But again, this is true. The set containing D, this only has 1 element, that's in there. And we could do something like this also. This 3-element set, 1, the set containing D, 2, the set C, 3, the set containing 5, 6, this is a subset of S. That is true. Okay. Okay. Just to make some things even more interesting. Okay, so these are just lots of different examples, and what we're doing is we're showing the main point of these examples is the following. When you use this symbol, here you mean an element over here and a set over here. And you're saying, question, is this element an element of this set? Yes or no? When you use this symbol, what you really have on the left side and on the right side is a set and a set. Not an element. Now again, a set can be an element, whatever. An element can be a set, etc. But the main point is, here you're asking, is every one of these elements also in the an element over there? Okay, so keep that in mind. But here's a very strange set, but totally legitimate. Consider this. The set T, which contains the element A, the element B, the element 4, and the subset A. That's a strange set. It both has the element A and the set containing A. Okay? So now we can say A is an element of T, because this element is in there. We could also say the set containing A is an element of T. We could also say the set A is a subset of T. Okay. And we can also say the set A, the set that contains the set A, is also an element of T. Okay? So we're just following the rules. The element A is in T, that's there. The set containing A is in T, that's there. The set containing A, because this A is here also, it's in there. And because this set containing A is also in here, so this is true too. Okay, great. Okay, so again, this section is called Some Special Sets. And so we want to talk about other special sets. So in particular, when you were in 8th grade, your teacher taught you about intervals. Intervals. These are parts of the real number line. Okay? And so you could have something like this. Here's the number A, here's the number B, and this is all real numbers between A and B. Okay? In some books they do it like this. Here's A, here's B with a filled in dot, and then you can talk about all these things. Okay, but then later on we're also going to talk about this. A till B. Those things in A, but not A, those things till B, including B. Okay? And in some books in high school, they did this like this. Oops. Okay. This was an empty circle. This is a filled in circle. And you can talk about all those things from A, but not including A, till B, including B. Okay? And we can write these as sets as follows. This is the set, by this I mean these two. This is the set A comma B, and we say this is those X, okay, member of the real numbers, such that A is less than or equal to X, which is less than or equal to B. So all those things, all those X between A and B, including A and including B. As opposed to that, we have this. This is A comma B, which is equal to those X, member of the real numbers, such that A is less than X, which is less than or equal to B. Okay? And of course we have other ones too. For example, A comma B with a round bracket. And you can figure that out. That's including A but not including B. So you'd have to swap these less than or equal to's. Okay? And then you can have A comma B not including A and not including B. So we might write that as x member of the real numbers such that a is less than x, which is less than b. All those numbers between a and b, not including a and b. Okay? So all these are called intervals, but we have much more of them also. Namely, we could talk about everything from negative infinity till a, including a. So if this is your real number line, and this is the number a, so this is everything from here until here, okay? And we never, whenever we have a negative infinity or a positive infinity, we write it like this with a round bracket. You don't include infinity. Infinity is not part of the real numbers, so you can't include it, so you make that round numbers. But basically, this is the set, okay, of x member of the real numbers such that x is less than or equal to, that's a square bracket, means a is in it, a. So anything less than that. Okay, and of course we could talk about round bracket negative infinity. We don't include infinity till a, and we could also talk about from a till infinity, and we could talk about from a with a square bracket till infinity. Okay, so this is what you have, a number a, and you're talking about all the way till there. Okay, you can write this also as those x member of the real numbers. Okay, and what do you want? You want those things greater than, square bracket, or equal to, so x, which is greater than or equal to little a. Okay, so these are the types of intervals that you can have. Again, infinity and negative infinity always get round brackets because you don't really include them. Okay. Now, we could talk about operations on these things, on intervals. So let me show you what I mean. Okay, take negative 5 comma 3. Okay, round bracket here, square bracket here, intersect 1 comma 4, round bracket. Okay. Okay, so what are these? So let me just say, this is an interval, this is an interval. This symbol, we're going to see more next section, is called intersection. This is those things that are in this set and in this set. So we could draw a picture of them. Okay, so here, let's draw a picture of it. Okay, here's 0, here's -1, here's -2, here's -5. Here's 1, here's 2, here's 3, here's 4. Okay, so -5 to 3 is all the things from -5, but not including -5, round bracket, all the way till 3, including 3. Okay, great. And with that, we can also talk about this set, 1 to 4. So it's 1, but not including 1, till 4, but not including 4, okay? And you can have all these things, okay? And now you ask yourself, okay, what's shaded both in black, that's in here, and in green? And the answer is all the things from 1, but not including 1, because it's not in the green, okay? Till 3, so from 1 till 3, are we including 3 or not? Anyways, yes, 3 is in the black, and it's also in the green, so we do that, 1 comma 3. Okay, so this is those things in this set, and also in this set. Okay, let's look at another example. Okay. We can also ask -5 comma 3, round bracket, square bracket, union. What is union? Those things in this set or in that set. Okay, 1 comma 4. Okay, and this is those things that are shaded in black or shaded in green. Okay, and the answer is -5, because this is not shaded. The -5 itself is not shaded in black. We have a round bracket all the way till 4, not including 4 because 4 is not in that green. Okay, there's another operation we can do. -5 comma 3. Okay, this we'll see next section. It's called symmetric difference. Okay, of 1 comma 4. Okay, and this is those things that are in this set or this set, but not both. Okay. Now let's just see what that means. It means those things that are in here, in the black, or those things that are in the green, but these things which are covered over twice, no, we don't include them. Okay, anything doubly covered, green and black, is not included. So this becomes what? -5 comma 1, square bracket. From 5 till 1, 1 is colored black. It is, because this is round, it's not colored green. So 1 is colored only once by black. Okay, but also from here to here. So union, now let's look. 3 is colored by black, because this is a square bracket. It's also between these two things, so it's green. So we don't include 3, okay, and we don't include 4 either. So this thing which is colored exactly once. So these are interesting operations. We'll see a lot more of them next class, but these are the operations done on intervals. And you're going to have homework problems like that too. Okay, great. Okay, there's the section is called some special sets. So there's a special set called the empty set. Empty set. Okay, and we denote it like that. We can also denote it like that. Okay, the empty set has the following property. Okay, I just want to say there's another set. Let's do it over here. It's another set called the set that contains the empty set. Now that's not the same as that. This set has one element. This set has no element. This set has no element. These are two ways of writing the same thing. Okay, we can also write this the same set as this. This is the set that contains the empty set. Okay, these two are equal. These two are not equal. Okay, so this is the empty set, and the empty set has the following property, and it's a little bit counterintuitive, but it's important. Okay, for all sets S, the empty set is a subset of S. Okay? The empty set is a subset of S. Okay? Let's see why this is true. What does it mean to be a subset? It means whatever is in here is in here. Well, there's nothing in here, so this is automatically true. Okay? So here's the following thing. Okay? Any student who is a billionaire in my class is automatically going to get an A+. Okay? Why? Well, it's a true statement because there are no billionaires in my class. But it's a true statement anyways, even, right, so we can make it. So this is called vacuously true. It's true because there's nothing in here. So this is like saying any person who can fly will automatically get an A+ in my class. Well, there is no person that can fly, so if they get an A+ in the class, that's true. So again, since this is here, so I just want to do a real example, 3, 5, and 7. The empty set is a subset of that. Now that doesn't mean that the empty set is an element, is an element of this set. Okay, hold on. This is not true, okay, because it's not an element, okay, but it is a subset. Again, what does it mean? Every element of this is an element of this, but not, this is not an element of that. Okay, so, although, watch this. This is the, for all sets, the empty set is a subset of that. Okay, but in this case, I wrote it like that, but it doesn't matter. It is an element of that. These two sets are the same thing. These are just two ways of writing the same thing. So in this case, not only is it a subset, it is also an element. Okay, very good. Okay, next. Definition. The power set of S, written like this, is the set of all subsets of S. So it's an interesting thing. We have this definition of a subset, and now we're going to look at all possible subsets of it. Okay, great. Okay, so let's look at an example of that. Okay, leave me space here. We're going to talk about the power set of the set that contains A and B. Okay. Here's a set, A and B. What are subsets of it? Well, one thing we said was the empty set is a subset of any set. So in particular we have that. Okay. Another subset is the set that just contains A. Another subset is the set that just contains B. And another, all three of these are proper subsets. But then we have a not proper subset, the entire set. And so we get that. Okay. The main point is all four of these are subsets of this set. Okay, and we're going to need this notion for later on. Let's do a better, a stronger one. The set that contains A, B, and C. Okay, and again, the order that I'm writing them down is not important, but you might as well write them down in some type of order. So here's the element the set that contains the set A, the set that contains the element B, the set that contains the element C, the set that contains the element AB, the set that contains the element AC, the elements AC, the set that contains the elements BC. And finally, so this is all 0 element sets, 1 element sets, 2 element sets, and then we have the entire set. 1, 2, okay, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, what about the power set of the set A, B, C, D? Okay, this has 4 elements. We're going to start them off. So the empty set, the set that contains A, the set that contains B, the set that contains C, the set that contains AB. Okay, and this goes on. Okay, all the way till the set that contains A, B, C, D. Okay, if you fill this out, you'll see that there are 16 elements in that set. Okay, so here we have 4, 8, 16. Let's try some of the earlier ones. The power set of the set that just contains 1 element. Let's see, what do we have? Well, again, the empty set is always a subset, and then the set A by itself. So this has 2. So if your set has 1 element, we have that. By the way, what's the power set of the empty set? What does the empty set, what subsets are there of the empty set? And the answer is just the empty set. So this is, the power set is the set. So that's the set of, it just has one set. Okay, but we see a certain pattern here. For a set that has no elements, there's a one element. For a set that has one element, there's two. For sets with two elements, we have 4. 3, we have 8. 4, we have 16. Okay, so let's write down this pattern. The pattern is as follows. If S has n elements, then the power set of S has 2 to the n elements. Okay, that's a pattern. We saw it for 0, 1, 2, 3, and 4. It works on forever. Why does it work on? Very simple. If you have an element in the set, then that element can be in a subset or it cannot be in the subsets. So take the element B. It could be in a subset and it could not be in the subset. The element A could be in a subset, could not be in a subset. The element C could be in the subset, not be in a subset. So here you have 3 elements, A, B, and C, and you have 3 questions with yes, no answers. Each one of those questions could have a yes answer or a no answer. So you have 2 times 2 times 2, 8 possibilities. Okay? If you had n elements in the set, you have 2 times 2 times 2 times 2 times 2, 2 to the n possibilities. Okay? Because each one of those elements could be in the set or not in the set. And when you're talking about, you want to list off all possible subsets, you have that. Okay, let's just write this a little bit better. Okay, it basically says this. I'm just, again, we're going towards symbols. If S has n elements, that implies that the power set of S, maybe we didn't have the symbol, this means number of elements of the set. The power set of the set has 2 to the n elements. Okay, let's again write this another way, even less symbols. We write it like this. The power set, less words, more symbols. The power set of S. So here's S, the power set of S, the set of all subsets. The number of elements to that is 2 to the number of elements of S. Okay, so that's pure symbols. This has one word in it. This is a sentence. 3 things saying the same thing, but this is more exact. No, it's not more exact. They're all 3 exact, but this is more shorter. And so we like that. Okay. Let's look at some examples that are interesting. Okay. So, here's an example. The power set of the power set of the set A, B, the empty set B, the set D, comma E. Okay. Whoops. Need another parentheses. Okay. Question. How many elements does this set have? Okay. So whenever you deal with something within math, with number of elements, or with anything, you always evaluate what's inside the parentheses first. So we're going to evaluate that. First we're going to evaluate this question. Whoops. How many elements does this set have? And the answer is 1, 2, 3. Repetition doesn't matter. We already counted B. So let's do that again. 1, 2, 3. And then the set containing DE. So this inner set has 4 elements. Okay, the power set of that is 16 elements. So let's just do this. This has 4 elements. This has 16 elements. And the power set of a 16 element set, okay, the power set of a 16 element set is something like 2 to the 16, which is about 64,000. About 64. 2 to the 10 is 1,024. 2 to the 11 is 2,000. 2 to the 12 is 4,000. 2 to the 13th is 8,000. 16,000. 64,000. Okay? So again, that's a big set, whatever, but the point is how this works. So again, repetition doesn't count, and this set is considered one thing. Now, compare this with another strange example. Okay, how about this? The power set of the set A, B, the power set of A, B, the empty set, and the set D. Okay. Okay, now we have to see how many, now we have to evaluate how many elements does the set. So we do the inside of parentheses first. So this has 1, 2, 3, 4. Okay, and what's this? This is very important. This is a set. This is a set of subsets of AB. So this is a set of subsets of A. So this whole thing is just one set. So watch what we have. 1, 2, 3, 4, 5. 5. So this has 5. So the power set of 5 is 2 to the 5th, which is 32 elements. So this set has 32 elements. Okay, so this is just a weird case. It has 32 elements. Okay, let's like I said, this class has a lot of different topics, and it's a prerequisite for a lot of different topics. So you're going to take a theoretical computer science class, you're going to take an information theory, they're going to talk about alphabets, codings, and words and things like that. So we have to do a little bit of that. And we'll see, there's lots of different things. Okay, definition. An alphabet is a finite, non-empty set of usually symbols or letters. Each one of the things we either call a symbol or a letter. Okay, so let's just do some examples. The Latin alphabet is A, B, C, all the way till Z. Okay, as opposed to that, you might have the Greek alphabet, which is, I told you got to learn that, is alpha, beta, gamma, delta, etc., etc. Okay, capital letters maybe also. Okay, you have okay, and you can have the Cyrillic language alphabet, and that has symbols like this, and this, and this, and that, and that, lots of others. And you can have the Arabic abajad, which is Aleph, B, T, Th, etc. Okay, so these are different alphabets, but for computer scientists, we're mostly interested in this alphabet, 0, 1. Okay, On a book on theoretical computer science, they spend a lot of time with this alphabet, A and B. Okay, and that's an interesting point, that in computers we can symbolize that we can describe everything with just two symbols. So that's pretty cool. Okay, great. So that's the definition of what an alphabet is. Okay, now definition of word. Definition, a word in alphabet. Sigma, that's a capital sigma. Okay, so that's the way we describe an alphabet. Okay, so now a word is a sequence of letters or symbols from data. Okay, is a finite sequence. Okay, main point. Here, order is important. Okay. CAT is a cat. TAC is a tack. Okay, they're not the same thing. Car is whatever. So the order of the letters is important. Okay, so ABA is a word in the alphabet AB. Okay, etc., etc. Okay, let's just go talk about it for a second. This are letters. This is ordered pairs of letters. Okay, two letters. Okay, by the way, in English, a word of one letter, there's only two words of one letter, A and I. Okay, how about words of two letters? So let's go through them. We have an, to, do, so, I'm sure there's a lot more. In, anyways, these are two-letter words. We might write this as sigma squared. Okay, and then there's going to be letters, words of length 3. We might write it like that. Triples of letters. We can write that as like that. There are a lot of English words that are triples of letters, but again, we're not talking about English yet. So just these are triples of letters. In general, we can write this sigma n. These are words of length n. They're n tuples of letters, and sigma star is the union of sigma n greater than or equal to 0. Okay, so these are words of length n, of any finite length. Okay, so this is the set of all words. Okay, in the book it talks about that, and it's called the empty word. Just like there's an empty set, so a word with length 0 is symbolized like that. Okay, great. So we have the definition of a language. We have the definition of an alphabet. We have the definition of a word. Now let's talk about what a language is. Okay. Definition. A language in alphabet. Sigma is a subset of words in sigma. Okay, so we have this progression. You start off with symbols, then you have words, then you have languages. Not every sequence of letters is a word in every language. Okay, just some interesting things. So Latin, let's talk about that. You have the alphabet is A, B, C, D, all the way to Z. Okay, and then you have, let's do it over here because we need more room. We have the set of all words in the Latin alphabet, and we have lots of different languages that correspond to that. English, is an interesting. French. French is basically English with a lot of accents. German. German is basically the Latin alphabet, except it has a symbol that looks like that. Spanish. Okay. Turkish. Turkish uses a Latin symbols. Okay, so that was changed in the 30s. They used to use Arabic symbols, but then they used Latin. It has nothing to do with Arabic. There's Malta, Maltese. Malta is an island in the Mediterranean. They speak basically Arabic, but the letters that they use is Latin letters. And Polish. Polish is a Slavic language, like Russian, like Bulgarian, like Ukrainian, but they use Latin letters. Okay, as opposed to that, let's talk about Russian. So Russian, I don't know. Okay, so lots of different languages use Russian. Well, Russian. This is the Cyrillic alphabet, and lots of different languages use that. Ukrainian, Belarusian, I don't know, maybe it is the same language. It's a variant of the same language, etc. Lots of different languages use that. Okay, Bulgarian. For Arabic, Arabic alphabet, Urdu, Arabic, obviously. Persian. Persian is not an Arabic language, but they use the Arabic letters to write their things. Okay. Okay. So those are different examples. Of course, we're not interested in those things. This is not a linguistic class. We're more interested in this type of thing. Subsets of zeros and ones. Okay. Okay. And that's enough about that. Let me just say one thing for the homework. In the homework questions, we're going to deal with this. This symbol, A/B, means A divides into B evenly. So 4 goes into 12. 5 does not go into 12. 3 goes into 9. 3 does not go into 22. Okay, you're going to need that for one of the homework questions. Anyways, that is the end of section 1.3. Hope you enjoyed. Then we do section 1.4. Okay.